Now let's talk about, there's something called the Muller-Breslau principle, and it is a way to qualitatively draw an influence line. You're still going to have to do a little bit of math to figure out the numbers, but it is a qualitative way of figuring out the shape of an influence line. So, the Muller-Breslau, I am not fluent in German, so I hope I said that correctly. Muller-Breslau principle states that the shape of the influence line is the same as the deformed shape of the member if the member is acted on by the loading of interest. Qualitative. Right? So we're talking about the shape, not the actual numbers. So if you want to know the shape of an influence line, apply the load of interest and see what it looks like. We'll show you what that means in a second. So the procedure for doing this is for a support reaction, remove the movement constrained remove the movement that is being constrained by that reaction. Movement being displacement or rotation. Right, reaction of interest. Apply that reaction of interest. And your displaced shape is the shape of your influence line. If you're talking about an internal stress, right, shear or moment, at a specific location. At a specific location. Break the member at that specific location. apply the internal loading. To each member part at that location. And again, your display shape is equal to the shape of your influence line. So I'm going to give you a couple of examples. Here we have, and this is all for a moving concentrated load, right? Just FYI. Here we have a vertical. We want to know the influence line for a moving concentrated load along a simply supported beam. We want to know the effect of that concentrated load on the vertical reaction at A. All right, pin to support A. All right, so let's see. I have my vertical reaction, AY. What kind of movement does that pin constrain, right? AY, because of the pin, my deflection in the X direction is 0. My deflection in the Y direction is 0. What movement does it allow? It still allows some rotation. A pin, right, allows rotation. So I want to know the vertical reaction. So I'm going to get rid of, what does that vertical reaction say? That vertical reaction means my deflection at Y is 0. And I'm going to say, meh. Now my deflection at Y can be some value. So I just turned my pin into a roller that has only a reaction in the horizontal direction, if I'm looking over here, right? All right, it used to have both. Now it only has the one. So if I apply that horizontal reaction, AY, there's nothing holding it down, keeping it from displacing, so it's going to displace up some distance. And have a deflected shape. Looks like that, right? I have some deflection, delta Y, I don't know. And a rotation, theta Z. So if I wanted to know what my influence line for that vertical reaction looks like, my influence line is like that, right? For AY. That means if I put my concentrated load right at A, I would have my maximum reaction force in the vertical direction at A. If I put my concentrated load over at the other end, I would have no reaction at A in the vertical direction. All right, let's look at, I kind of want to make that blue. I'm going to do that. Okay, now I have a cantilevered beam. I've got a horizontal reaction, AX, a vertical reaction, AY, and a moment at A. At A, this support, right? Delta X is 0, delta Y is 0, and my theta at Z is 0, right? No displacements, no rotations. And I'm like, okay, how's that vertical reaction work? What is that influence line for that? So now I'm like, okay, let's allow vertical displacement. So now I kind of look like this. I have a roller that allows movement in the vertical direction, but it doesn't allow movement in the horizontal direction, and it doesn't allow rotation about Z. So if I apply that vertical reaction AY, what happens is the whole thing just shifts up, right? Shifts up some displacement delta Y. But it can't go side to side up, and it can't rotate, so it's still that straight line. So my delta X is still 0, my theta Z is still 0, but my deflection in the Y direction isn't 0. So if I were looking at this influence line, what does this mean? It means no matter where I put that concentrated load, my vertical reaction is going to be the same. Moment, not so much, but my vertical reaction is going to be the same, right? Right. So let's talk about moment. We got the same thing going on here. Here's my cantilevered beam. It has a vertical reaction, a horizontal reaction, and a moment reaction. And that means it constrains deflection in the X direction, deflection in the Y direction, and deflection in theta rotation about Z, right? Now I'm like, I want to find the moment reaction at A, the influence line for that. So I'm going to take it out. So now I'm going to allow rotation. And I have my vertical reaction at A, my horizontal reaction at A, and I'm going to apply that moment at A. So what happens, I'm going to rotate that thing around that pin, right? I just changed my fixed support to a pin support by taking out that constraint against rotation. Oops. So I have some type of rotation z, right? If I want to look at the influence line for my moment at A, the closer I put that concentrated load to A, the smaller that moment is. Makes sense, right? The closer you get, the smaller the moment arm is. So it's going to decrease. My maximum moment occurs if I put my concentrated load way out at the end of the beam. So those are examples of taking out your reaction constraint and finding the displaced shape, right? If I look at, now I'm going to look at some internal stresses. Right? I want to look at shear at this location right here. I'm just going to call it V, right? Well, V at this location, C, right? So I cut the beam at C, right? This is still the point C. That's C. This is point C. And I apply a shear. Right? If I'm looking at if I break it into two pieces, I apply shear here and I apply shear here. What I've drawn there is a roller, right? If I apply shear, you might be able to tell this is going to go down and that's going to go up. So I know qualitatively, if this is my point C, oops. If this is my point C that I decided to look at, if I want to draw the influence line, it's going to look like that. Which looks like what we did earlier, right? Now what about a moment at a random spot? I'm going to choose a moment at a random spot D, right? Oops. I'm going to break my beam. I'm going to put it, basically it's going to look like a hinge, right? Make a roller. at C, make a hinge at D. Now if I look I'm going to break it into two pieces. I'm going to apply a moment right there. This is the, what would that look like? If I applied that moment, it's still holding on over at that support, so I would just rotate those two little pieces up if I applied a moment. So if I wanted to look at that, I don't know, D is like what, right here? If I were looking at my influence line, it would look something like that. To get my maximum moment at that point D, I would have to put my concentrated point, my concentrated load at point D. So that is how you can use the Muller-Breslau principle to qualitatively draw your influence lines. Now you'd still probably need to calculate the shear or the moment or the reaction. You need to calculate these values, right? And you can use the way that we talked about earlier, just breaking right there. And the reaction there, right? That's how you calculate the values. But now you don't have to calculate the function. You just need to draw it and then say, oh, I need to calculate it at these certain points, right? You need to calculate it here, you need to calculate it here. Down for this internal moment, you only have to calculate it right there at D. Okay? So that is how you can use this principle to draw your influence lines.